Yeah, welcome everybody, and I hope it's okay. I slightly changed the title, but the content will be the same. So I want to tell you today about what we do with polymers for light-driven catalysis. And there will be two types of catalysis. One is proton reduction, so in the end evolution of hydrogen. One is water oxidation, so evolution of oxygen. And especially the latter case is much more challenging. And the biggest question we always get asked is, what does this reaction do with the polymers we provide, and how does it actually change structure? And I will have one or two slides also on that. But first, what you see here are the people who are actually doing the work, mainly in the bottom. So Philip and Katrin were a lot involved in designing the base polymer. Yuri, Nia, just switch on the Laserband, that's maybe. So Yuri, Nia, Vachu, and Tolga, and also Afshin were really the PhD students who were part of the project in which framework all this research was done, to which I will come in a few minutes. I take the liberty, because the audience is probably very diverse and spread all over Europe, so I thought maybe one slide on Jena is not too bad. So we are located along the river Saale, and you see here, of course, Germany. Then this is you say it another land, but it's a different district in Germany. So we have 16 districts, which are sometimes very different in how they do certain things. And so this is Thuringia, quite central in Germany. This is Jena then in Thuringia, and that's how Jena is located along the river Saale. It's quite humid, it's quite warm for Germany. What you can know about Jena is that two big companies come from here. It's Schott and Zeiss, that at least all chemists will have come across. One chemist you might not know, but who was very popular in Jena, is Friedrich Göttling, who was one of the first doing experimental lectures, and in the end was the first chemist in Germany who had an independent professorship. At that time, chemistry was typically associated to medicine or to pharmacy. And then last but not least, what probably all of you associate with Germany is something that originated in Thuringia, and that is fried sausages. So bratwurst is something that originally comes from Thuringia, honestly, actually rather here. That's the first time something like a bratwurst has been mentioned in the book and probably eaten. Coming from that, so we now look a bit on what our group is actually doing. So we are polymer chemists. We do a lot with charges and how we control charges in polymers. And there's one way that most of you will know, and that is by changing the pH value, and by that changing the charge balance in the system. We also have cases where we do that by light. Speaking of photoacids, photobases that are not protonated or deprotonated in the dark, but change their acidity or basicity when you shine light. So these are two ways of how you can control the net charge in a polymer. And where is this of interest? Well, we control surface charge with that. We look into if something adsorbs or desorbs from a surface. We modify the surface of membranes or nanoparticles. And important for today, we can design host environments for catalysts and for photosensitizers. So the project in which basically all of what I'm going to show in the next 10 to 15 slides has been done is called Catalysis, and that's a collaborative research center that is mainly located on the axis Jena and Ulm, so here across Germany, but also has satellites in Mainz and in Vienna. And the idea is to use soft matter as a host environment for light-driven catalysis. Soft matter, as we all know, is very good in making changes in degree of swelling or polarity or charge with relatively subtle changes in environment. And that's what we want to exploit. So the task is to create a defined local environment. And if you talk to many people doing light-driven catalysis, they often work in organic solvents. We want to go to water, and we want to move away from noble metals, but that can only be done as a whole in a consortium. Soft matter role can also be buffering, providing certain regimes of pH value, ionic strength for a certain catalyst over longer time. Soft matter allows you to mildly anchor a building block and to control the distance or the orientation. And with that, what Catalyte tries to do is to devise blueprints for hybrid materials that can do light-driven catalysis, and also implement exchange of building blocks. You can call that repair strategies. That is the essence in a way. And the reactions we look at are typically electron, or let's say redox, photoredox catalysis, in the sense that you have a photosensitizer here abbreviated with TS that absorbs light, ideally in the visible spectrum, then gets to the excited state, is, for example, capable of transferring an electron to a catalyst, abbreviated as CAT here, and then we have different reactions. On the reductive side, we look at proton reduction, so HER is hydrogen evolution reaction. We reduce CO2 to CO, for example, but we also have an oxidative side that, for example, oxidizes water to oxygen or oxidizes an alcohol to a carbonyl group. These are separated half reactions we, in many cases, look at. And of course, the vision is at some point to also combine that. So questions we often get, or we often address, is what is the role of the matrix? Does it also participate in the reaction? And of course, as I said, at some point you want to combine half reaction. The approach we often have are polymers, or block copolymers, or graft copolymers, where the blue part controls morphology, solvent resistance, if we have to use something that is not just water, and any response, any adaptivity we implement in the red part. Then, of course, you can attach a linker group or an anchoring point, and you can, by the comonomer composition in the red part, you can introduce attachment modes for a catalyst or a sensitizer. That can be electrostatics, which we often do, can be supramolecular, like a pyridine or bipyridyl linker, or it can be really covalent bond, sometimes also reversible covalent. It all started when I was actually still quite young and had more hair, and when I was doing an Erasmus internship in Lund. And what you see here in the bottom right corner is the molecule in amido acrylate that we used in solvent-free hack reactions in the ball mill. And the first time I've done that was on a 10-gram scale, a 3-step synthesis starting from serine. And then, not knowing much about polymer chemistry, I left it on the bench over the weekend. And in the morning of Monday, I found a stone that was insoluble in everything, or in anything. So that told me this thing can polymerize. And that's something I then came back to when I moved to Jena. I said, these are actually interesting polymers. If you take this amido acrylate and you polymerize it, in the meantime, we can do that by basically all possible radical polymerization methods. Then you get this dual protected polymer that you can deprotect, sometimes orthogonal, sometimes simultaneous. That depends really on the conditions and on the protective groups. And then you get something that I was debating a lot with colleagues how to call that. It's a polyampholite, but it's also a polyswitter ion. So in the end, it's kind of a polyampholite with Switter ionic character. So you have at high pH a poly-N ion, at low pH a polycat ion, and the interesting part is really that you have a broad range in between where it behaves like a polyswitter ion, but has an excess plus or minus charge. And of course, you have an isoelectric point that is highlighted here with 7. I have to update that graphics. It's actually between 5 and 6. So this is something I really have to change. The interest in these polymers is that we have a high charge density, probably one of the highest charge densities. We can invert charges that allows to mediate interactions, and you have a broad regime where it acts some kind of polyswitter ionic. And you can use it for chemistry. That is when Johannes came into play, who was a PhD student who moved from Freiburg to Jena, and he said he would really like to use this polydihydroalanine, or the version where the methyl ester is still not deprotected, as a polymeric reaction platform. In a sense, modify then the amino groups and create a range of graft copolymers. You can do that in 2 ways. One is that you use nucleophilic attack on an epoxide to do that, or you use some sort of a Michael analogous reaction and you introduce different R groups here. And he has done that for quite a range of hydrophobic side chains. So here the red numbers always tell you the degree of functionalization that's possible. And yes, the acrylonitrile, you can do more than 1 unit per amine. So 130 means on average 1.3 units per repeat unit. That is quite nice. And then depending on which side group you introduce, you can use that for sensing or for surface modification of carbon nanotubes. Those were the first things we have done with those graft copolymers. More interesting it became when we went to hydrophilic side chains. For example, NiPAM units that impart thermoresponsivity, or sulfonates, phosphonates, or carboxylates that makes very complicated titration patterns, but gives you a lot of anchoring points for charge mediation. And of course, we can also implement short units of oligo or polyethylene oxide, and that makes those polymers, despite the charge, basically soluble in almost anything. So you have charged polymers that you can dissolve in organic solvents. That is actually quite cool in some cases. So one thing we have done with these graft copolymers is we used them for sensing. So here you see the graft copolymer, and then what we wanted to see is actually either a difference in cloud point or a difference in surface plasmon resonance upon introducing, for example, a silver nanoparticle. So this would be the readout, and the input could be changes in pH value, changes in temperature, or the presence of certain metal ions. So how does that work? In this particular case, you had the same polydihydroalanine backbone. You have NiPAM grafts, but not polymer, just monomeric unit. And interestingly, if you have more than 40–45% of the repeat units grafted with NiPAM, you get a thermoresponse that is actually quite close to polyNiPAM and depends on the pH, so on the charge density of the polydihydroalanine backbone. That was a bit surprising, but it works. So what we've done here is then you see in this figure, you see the cloud point of the graft copolymer versus the ratio of carboxylate that is down here over metal. So what we did is we added small amounts of metal cations and we measured the cloud point temperature with the idea that as soon as you start impacting the solution structure of the graft copolymer significantly, the cloud point will change, and use that as a detection limit for metal cations. So for example, for copper, this is quite sensitive. So if you count that, so here in black, if you have one copper unit for one copper atom for 230 something carboxylates, you have a cloud point change of 7 degrees, which is measurable. So you can use that to detect small amounts of copper. It is a bit less sensitive for lead or for cobalt. We've also tried nickel, so there are many metal cations that actually change the conformation and change the solubility of these graft copolymers. But now coming to the matrices. Again, you need a defined nanolocal environment, you need anchoring sites for catalyst or sensitizer attachment, and we have 3 classes here. We have graft copolymers, which I just introduced. We have colloids, where you take the concept from the graft copolymer just as the hydrophilic shell of the colloid. I will not show anything about that today. And we have a third, I was about to say a third level of escalation or third level of complexity, where you can actually create 3-dimensionally porous structures that on the surface of the pores have a similar concept. You have charged polymers, and then you can implement these catalyst sensitizer combinations under flow conditions in a membrane. But I will also not show that today. I will rather focus here on the left part and go a bit in direction of hydrogels. The motivation for that is here on the left-hand side. You really talk about solubilization, local concentration increase. In the middle, you can actually start to talk about heterogeneous catalysis. And on the right side, you really can talk to an engineer and think about how to implement that into a flow reactor. So these are different levels of transfer, of possible, also scale up in a sense. So that is also the beauty of working in a collaborative research center, that we have engineers on one side who are really happy with the membranes, but we really have mechanistic questions that you rather would solve on the left side with graft copolymers. So that is, in that sense, the beauty of polymer chemistry, that you can go to different levels of heterogeneity and complexity at the same time. To give you a first example, here you see a simple graph copolymer, again, the same polyampholytic backbone, PEG side chains. The PEG side chains are for solubility, the backbone is for anchoring sites, or acts as anchoring sites. Our model system is already noble metal free, so it's a molybdenum sulfide as a proton reduction catalyst, and it's a body P dye as a sensitizer. So the body pi absorbs around 530 nanometers, transfers then from the excited state an electron to the catalyst. The molybdenum sulfide catalyst then reduces a proton. And this is a quite active system, but it would not work molecularly in water or in water-methanol combinations where you have more than 30% water. So now the idea was to combine that with this graft copolymer, and the model looks a bit like that. So you have the graft copolymer, you have the side chains, PEG here in red, and then depending on whether you have a positively charged or a negatively charged anchoring site, you find either catalysts or sensitizers along the backbone. It's simplified, but that's how we think it is. Then, of course, these chains are not molecularly soluble anymore, and they start aggregating, forming relatively loose colloidal clusters. Size range is 10 to 30 nanometers, but they are colloidally stable. And then you can start doing catalysis here. In a sense, you irradiate with light, you measure from the gas phase, you take samples, measure with HPLC, with GC, excuse me, and basically determine the amount of hydrogen. And you can see, depending on how the hydrophobicity of the so this is a phenyl group, like the one up here, but you can have different substituents down here on the body pi. If you play with the hydrophobicity of the body pi sensitizer, you can tune the catalytic activity. And what you see here is actually quite nice. So the tons are high, so turnover numbers. I would rather also stress here the turnover frequency is very high, so that is quite active also in comparison to other hydrogen evolution catalysts. And we could show that in combination with the graft copolymer, you can do that at different water-methanol ratios, and at 50-50, this seems to be the optimum. But this optimum would change depending on the solubility of the sensitizer. So you get into some sort of a molecular toolbox, how you can combine these things. And in a sense, that's the first step. So if you think about other examples of such catalysis, they often contain either ruthenium, rhodium, or iridium, so we can move away from that to more abundant systems, and we are not yet fully in water, but that I will show a bit later. Then Tolga came into play. Tolga's PhD thesis was really now to take this polydihydroalanine and move one step further to materials. And there's a very simple step. You take not a monoglycidyl ether to modify, you take a bisglycidyl ether. And by that, you create very nicely and transparent hydrogels. And those hydrogels, depending on the cross-link density, they still feature everything you have learned from the polydihydroalanine as a polymer. That means you have hydrogen bonding, you have charge inversion, you have a polycationic hydrogel at low pH, a polyanionic at high pH, and something in between in the pH values in between. So then we started also loading that with complexes, in a sense, first with the sensitizer. And the most studied photosensitizer of the world, I want to say, is ruthenium tris-BPY. So that is really the fruit fly of light-driven redox catalysis. Many people use that. So if you want to introduce a new matrix system, you use something that people know. So we started with ruthenium tris-BPY. And you can see here the gel nicely gets yellow if you load that. You can quantify the absorption spectroscopically, so how much milligram per gram you can load with the sensitizer. And even more, you can also go to pH 2 and basically kick out the sensitizer again, because if you invert the negative charge from the gel to positive, the complex is positively charged, then you can wash it out again. And that is the first example that you can actually exchange building blocks in these gels. You can quantify the absorption depending on pH, and you see we have kind of a sweet spot at pH 8 to 9. So this is an example where you can show that we really can move towards repair strategies, exchange of degraded building blocks. But can these things do catalysis? And the answer is yes, they can, and this time it's really in water. So hydrogen evolution, you might have a déjà vu. So that's the same catalyst. So after the ruthenium sensitizer, we load the molybdenum sulfide into the gels. And depending on the ratio of catalyst to sensitizer, that's the value here on the bottom line, you can get different amounts of hydrogen evolved. Why do I not write tons here? That is because you assume that all the catalysts participate, but you don't know. It's clearly a diffusion process now that whatever sacrificial agent you use has to diffuse into the gel. And the question is at which catalyst it does react. So you cannot really say that all the catalysts participate. And if you cannot say that, you cannot really calculate a ton. Well, you can, but it clearly is a bit wrong. So that's why we rather, for such a system, give a quantified amount of hydrogen. And that's why you see micromole per gram here. And you can also see that it depends a bit on the type of sacrificial electron donor you actually use. Keep in mind that is always a half reaction we show, so the proton reduction only. But the same matrix, or the same ruthenium-loaded gel, you could also use for a more challenging system. Then that is a water oxidation catalyst, cobalt phosphor tungsten POM from the group of Carsten Streep in Mainz. And here we can see that it is, here you see that in the hydrogel, this catalyst is more active than in solution. That can be solubility problems, but we also have hints that the degradation of the ruthenium photosensitizer in the gel is slowed down compared to solution, so the photooxidation of the sensitizer itself. So the gels are also active in water oxidation, but there's always a but. You can see here on the right-hand side, those are NMR spectra of the gels. And that is before the oxygen evolution reaction. So you see clearly the signal for the CH2 groups of the PEC bis-glucidyl crosslinkers. And I mean, 27 days is a long time for such conditions, but you can see that they disappear. And you also realize that for the gel, it gets a bit more wobbly and it swells more, and at some point it disintegrates. So it's not only the sacrificial agent that gets oxidized here, it's also the gels, so the crosslinks that get oxidized at some point. So we might have to, it's not during the first 1-2 days, but you might want to use that for longer. So we really have to think about different crosslinkers here. My last example is now also with these gels, we of course wanted to move away from noble metal building blocks or noble metal catalysts or sensitizers. So Tolga did one more modification step to increase the density of cationic charges. So here we have a trimethylammonium glycidyl ether that partially modifies the polydihydroalanine. Then we do the cross-linking with PEC bis glycidyl ether. And then the beauty is really you can dry these gels and re-swell them also in organic solvents, like in DMF, like in DMSO, like in THF. And that allows you then to attach also a sensitizer here from the group of Kalina Peneva, a rylene-based sensitizer that is noble metal free, but that would not dissolve in water, at least not molecularly. Then you can load the gel with the sensitizer. Then you get a nicely purple gel, not yellow anymore, but purple. And that is how we think the sensitizer attaches. And then another déjà vu, we again load a catalyst, again proton reduction catalyst, again the molybdenum sulfide. And then we have a gel that contains noble metal free catalyst, noble metal free sensitizer. And also these gels are quite active in hydrogen evolution. You see again here on the ratio, depending on the ratio of sensitizer to catalyst, so decreasing ratio, so less sensitizer gives more hydrogen, probably because at some point the sensitizer starts aggregating. And you also see one of the reveries here forced us to also calculate a ton. So we have both the micromole per gram, which we wanted to report, but we also had to include a ton, assuming that all the catalysts are active. And even more important, you can reload. So if you do more cycles, you see that the activity in hydrogen evolution goes down with cycles because the catalyst degrades, maybe something else is happening. And then you can load fresh catalyst, that's the blue spot, and basically reactivate the gels in the range of the arrow to the original activity. Of course, you also do some blank tests, like in a sense you don't have leaching of the sensitizer that you can test by UV spectroscopy. We also have no hydrogen reduction production activity in the solution without the gel. So that is a quite intriguing system in our opinion. So there's no magic behind designing these matrices. You just need a good base polymer that allows you to introduce anchoring points, do some halfway flexible chemistry, and is adjustable in charge. Reversible adsorption is our repair strategy, and we can clearly show that we can move to water and to noble metals. The big question for all these systems is, can you compare across systems? And that is often really, really difficult. We try. If you take this combination of this really very often used hydrogen evolution cap, molybdenum sulfide, you can show that with graft copolymers, you can combine it with almost any organic photosensitizer. It's longer active, and you can go to higher contents of water. If you go to colloids, which I've not shown today, you can get to turnover frequency numbers that you have never, or at least to our understanding, have never been reported for homogeneous conditions, at least in the beginning. If you go to gels, you can repair or exchange catalyst, and you can really also go to fully aqueous systems and noble metal free. And that I have not shown today, you can also go to flow-through conditions. So the vision of Catalyte was always you have some sort of a thing in hand that is a matrix, a catalyst, a sensitizer. You throw that into water, put it in the sunlight, and it starts bubbling. And you can see down here, and this is indeed the case. That's a porous membrane loaded with polymer, loaded with catalyst, loaded with sensitizer. You put it in aqueous solution at the right pH, I have to say, at around pH 5, and it starts bubbling hydrogen. So this is possible, and you can really put these stacks also in reactors. I've mentioned some of the people. You've seen pictures of the people in my group who actually do the work. We have a lot of collaborators because until a few years ago, I've never done catalysis, not even light-driven catalysis. So this was really new for us, and we learned a lot, sometimes painfully. I think what we can really say is catalysis. This is a picture from a stay I had in Le Mans, and I would substitute here life and cat. So if you do catalysis, you can really change conditions with polymers. And with that, Sergey, many thanks for inviting me to this conference. I'm curious also to see some further talks today, and I am happy to take any questions.